Think about the physical infrastructure required to keep a global enterprise online. You are dealing with thousands of routers, switches, and endpoints scattered across continents. Managing a network of this scale manually is a mathematical impossibility. To impose order on this system, engineers rely on 4 pillars of network management, known as OAMP. The first 2 are operation, which focuses on keeping the network and its services running smoothly on a daily basis, and administration, which tracks exactly what resources exist and how they are assigned. The final 2 are maintenance, covering the physical or software-based repairs and upgrades, and provisioning, which handles configuring specific resources to support a new given service. Executing these 4 pillars requires a constant stream of telemetry. Network administrators collect this data through several mechanisms, including software agents installed directly on the infrastructure, synthetic monitoring that simulates network transactions, historical activity logs, and packet sniffers. Pulling telemetry from thousands of devices creates an immediate engineering problem. A network might consist of Cisco routers, Juniper switches, and Dell servers, all running proprietary operating systems. Gathering cohesive data requires a universal language that every piece of hardware understands. Without a standardized, vendor-agnostic protocol to bridge these differing architectures, enterprise-scale management collapses into unreadable, isolated silos. The solution to that translation problem is the Simple Network Management Protocol, or SNMP. This is the Internet Standard Application Layer Protocol, designed specifically to manage devices on IP networks. SNMP provides independent management. It operates exactly the same way whether querying a high-end enterprise firewall, a basic Linux server, or a generic network printer. The standard achieves this uniformity through 3 core components: an application layer protocol used to transmit messages, a database schema that structures the information, and a strict set of data objects representing the device's exact configuration. The goal of this architecture is to minimize the computational weight of management functions. The protocol remains flexible and extensible, ensuring it can support future hardware types without requiring a rewrite of the underlying standards. Since its initial draft, SNMP has undergone massive architectural revisions. Engineers have iterated the standard from version 1 through version 3 to resolve severe performance bottlenecks and security vulnerabilities present in early network designs. SNMP's rigid abstraction forces all hardware vendors to speak the same language to centralized administrators. An SNMP environment operates on a client-server model. The network management station acts as the manager, controlling network elements. On the receiving end is the agent, a software module running on the equipment, maintaining a local database of its configuration. While SNMP is classified as an application layer protocol, its speed and efficiency rely entirely on how it handles traffic down at the transport layer. This diagram shows the transport mapping. The NMS client initiates communication by sending active requests to the agent server using UDP port 161. When an agent sends an unsolicited alert, a trap, back to the NMS, it transmits that notification on UDP port 162. By utilizing connectionless UDP ports instead of the heavier connection-oriented TCP protocol, SNMP avoids the overhead of complex handshakes. This enables high-speed asynchronous monitoring that won't consume the network bandwidth it is trying to measure. To understand how the agent actually stores its internal data, we have to look at the Management Information Base, or MIB. A MIB is not a traditional flat database with standard tables and rows. It is a strict, hierarchical namespace designed to map out the exact structure of a device's hardware and software subsystems. Within this hierarchy, every specific piece of readable or writable data is assigned an object identifier, or OID. An OID is a numerical sequence that acts as the exact mathematical address for a variable. This chart shows the standardized namespace structure. The path starts at the root, descending through ISO node 1, org at 3, DoD at 6, Internet at 1, and down to MIB2 at node 1. This node contains 11 operational groups organizing essential metrics. Network administrators do not typically memorize these long numeric paths. Instead, they rely on terminal tools to interact with these groups using human-readable text. In practical application, like the setup in your Lab 5 exercises, you use commands like SNMP translate. This utility takes a text string, like sysuptime, and converts it into its exact numeric OID equivalent, in this case, .1, .3, .6, .1, .2, .1, .1, .3. The MIB structure bridges the gap. It provides readable labels for human engineers while generating the high-speed numeric routing required by the protocol itself. The original implementation, SNMP version 1, functioned but suffered from structural limitations. It supported very limited data types, lacked hierarchical error codes, and was highly inefficient when an NMS tried to pull large datasets. Retrieving a 2,000-entry routing table required the NMS to send thousands of individual requests. This constant back-and-forth exchange consumed extensive bandwidth. SNMP version 2 solved this bottleneck by introducing the GET bulk request. Instead of asking for data one line at a time, the NMS issues a single GET bulk command, and the agent packages and returns a massive, continuous block of management data. Version 2 also introduced the inform request. This operation allows manager-to-manager communication, providing guaranteed delivery acknowledgments between central servers. To prevent errors when changing device configurations, version 2 redesigned the SET request by implementing a conceptual two-phase commit architecture. In Phase 1, the agent performs a series of rigorous checks to ensure the incoming variables are valid and the requester has permission. Only if all checks pass does the agent proceed to Phase 2 and actually execute the SET operation on the hardware. Version 2 eliminated the major data retrieval bottlenecks and improved operational safety, but it still relied on community strings for authentication, leaving the network's telemetry unencrypted. SNMP version 3 initiated a structural overhaul of the standard. It moved past simple performance enhancements to directly address the protocol's lack of encryption and authentication, focusing entirely on data confidentiality and integrity. This diagram illustrates the SNMP entity architecture, separating managers and agents into an engine and applications. The engine's routing core includes the dispatcher and message processing subsystem. Its security core contains the security and access control subsystems, handling authentication, encryption, and strict object-level permissions. Above the engine sit 5 dedicated application types: command generators to request data, command responders to provide access, notification originators to send traps, notification receivers to catch them, and proxy forwarders to route requests. By decoupling the physical routing engine from these highly specific applications, SNMP version 3 guarantees that strict enterprise security rules apply uniformly to every command passing through the network. As you review for the exam, map the 3 major versions of SNMP directly to the specific historical problems they were designed to solve. Version 1 is the baseline architecture. It established the core manager and agent UDP framework, but failed at enterprise scale due to extreme packet iteration during large table retrievals. Version 2 is the performance architecture. It accelerated data gathering through the GET bulk request and protected device configurations using the two-phase commit SET operation. Version 3 is the security architecture. It introduced the modular entity structure, dividing operations between the engine and applications to enforce confidentiality, integrity, and authentication. Yet beneath the complexity of the newer versions, the objective remains unchanged. SNMP exists to execute the 4 core network management pillars: operation, administration, maintenance, and provisioning. When executing your Lab 5 exercises, keep in mind that the protocol doesn't run in a vacuum. You must manage localized service states, like stopping the DHCP daemon, before your SNMP testing can yield accurate IP configurations. You will also need to install the net SNMP utils package. This is the toolkit required to manually test MIB OID translations directly from the Linux command line. Tracing that data flow from a human-readable terminal request down through the UDP transport layer and into the precise numeric node on the MIB OID tree reveals the underlying logic of modern network management. Modern network management relies on programmable, standardized engineering. SNMP is the protocol that makes that scale possible.